They're collectively called, what are they called? Nucleons. Okay? I mean, we know it's the nucleus. You know, sometimes they like to make up new words, which is the same exact thing. It says here that the atomic number, oh, I know I talked about the atomic number when it comes to this as well last week. The atomic number, which is, and I know that I didn't give you a lot of space, which is at the bottom, depending on how you're going to look at it, right? Let me come over here. I'm going to come to this picture. They have the atomic number over here, which is at the bottom. Going into nuclear chemistry or talking about radioactive decay, almost always they write it this way. I'm not saying that is the way it's written, because on a periodic table, a lot of the times the top number is the atomic number on a periodic table, and we know that it's the atomic number because it's a whole number, and the atomic mass, I said last week, is a decimal number, right? The atomic mass, when written in this situation, is going to be the top number. Looking at the periodic table, it would be the number that has the decimal with it, right? Because it's an average of all of those combined together, okay? So it says here that the atomic number, which is at the bottom, it says that it's the number of proton. It's that proton number that is never going to leave, kind of like your driver's license number. Once you get a driver's license number, it's going to be the same number for the rest of your life. Never going to change, no matter how old you get, no matter how short your hair gets, no matter how much weight you lose, it's the same exact number. It says here, though, the atomic mass, I'm coming back over here, for this situation, not like a periodic table, but in this situation, which is the top number, this number is going to be the neutron number plus the proton number that are going to be added together. Now, for this situation, as we're looking at this, it's going to be a whole number. I don't want anybody to freak out. On the periodic table, Miss Munson, it's a decimal. I do know that, but I do also know that in chemistry class, you probably talked about how you're going to either raise that number up or you're going to leave that number as alone as it is, because it was like 15.9999 is the atomic mass for oxygen. So most of us just raise it up to the number 16, right? So this is how we're going to do the math, so that way we can figure it out. Pretty easy, cheesy math when it comes to that. It says here that the number of electrons is equal to the number of positive protons, and we consider in chemistry that all atoms are considered to be electrically neutral. Electrically neutral. Now, I do remember, and I hope you remember that, well, you know what? Atoms don't stay electrically neutral, right? They end up having a charge, and you were taught, or you were told probably about cations and anions, right, whenever they have a charge. Now, there are some atoms that do completely stay electrically neutral, that never become ions. They're over there in group 18, right? Those noble gases, they're always going to be electrically neutral and never, ever, ever, because they have a perfect amount of number. They don't need anybody. They just leave themselves alone, right? But other than that, truly, the true answer over here is that all atoms are going to end up becoming an ion except for group 18. But we do, in chemistry, consider them all to be electrically neutral. Okay? Making sure I said that enough times. Now, the next word over here, which has probably been a while since you talked about this word, isotopes. Again, it's kind of like a review, so sorry. Isotopes. It says isotopes are atoms of the same element, which means that they have the same number of protons, right? Because they're the same element. They have the same driver's license number with different numbers of neutrons. And this is what I talked about last week, that this is when our atoms become heavy. They get old, and when they age, they're going to gain neutrons, and neutrons is going to make them gain mass. And that's the reason why that atomic mass number is a decimal point. Next part over here says adding the neutrons to the nucleus, it says here, can actually cause it to become less stable. There's only so much you can add. I mean, Thanksgiving, Christmas, whatever holiday's coming around, and you can keep adding so much food to your paper plate, but it's gonna be a point where that paper plate is gonna just collapse. It can't hold all of your food that you wanna put on there, right? Let's say this is Thanksgiving lunch, Thanksgiving dinner. If you don't have an actual solid plate, then with your paper plate, depending on what type of paper plate you got, there's a good chance that it's going to become less stable as you continue to add more mass to it or more neutrons. Same thing when it comes to atoms, same exact thing. So it says here that we call this nuclear decay. And nuclear decay occurs all the time on its own. It occurs all the time, on its own, where my atoms are going to end up becoming less stable, and the reason why atoms become less stable is because they end up with more neutrons. It says here, though, then writing these isotope symbols, or we need to go ahead and make sure that we can write those isotope symbols correctly, and this is how we would write it. We would write, let's say, whatever the element is. So when writing an isotope symbol, again, I can definitely go grab a periodic table. I did print some out for us last week, but just so we're all on that same page when it comes to, where did I print those signs out? You see them printed at one? No, not the bucket. Oh, under the bucket? I printed a whole bunch of periodic tables just for this class. And I was like, you know what? Oh, this one. I'm gonna use that one though. Do you see them one? You don't see them there? Alright, let's see. I wonder if I left them in the office. And I was trying to do a good thing. Probably left them in the office. That's all right. I don't have it. I need this one. All right. I know I printed those suckers out. Maybe they're over here. Let me do a double check over here because I really wanted to give everybody a periodic table. No. That's all right. All right, so just a quick looking at this. Now, when we look at the elements here on the periodic table, we don't consider these elements to be isotopes. We consider these elements right here to be a neutral atom, having the same number of protons as they do electrons. Now, we know in chemistry, though, that every single one except for group 18, or group 8, however you call it, are going to eventually become an ion or a charge because they're unstable, they're unhappy. They need more negative electrons, or they need to get rid of some negative electrons. But we definitely know that group 18, they're happy, they don't need to gain more electrons or give up any electrons at all. Now, we just call these plain neutral atoms. But when we're looking at, or when we're writing an isotope atom, in that situation, we're going to make sure that we put the atomic mass on top, and it's going to be a whole number. I don't know, do I need to write that for any of us? It's going to be a whole number, even though over here, looking at the periodic table, even though group 18, for example, they're going to always be electrically neutral, they still have a decimal point there, okay? And they still have a decimal point. But here, when we're talking about, or we're writing out what we consider to be isotopes, we write the mass number on the top, and it is a whole number. Please don't get confused. I do have students that get confused. It is a whole number, and it is the mass number. We consider that to be an isotope. Now, isotopes are also written like this. For an example, carbon-14. Carbon-14 is considered to be an isotope. Well, let's go ahead just to make sure if we don't call. Here's carbon on the periodic table. There he is. And carbon-14, when we look at the periodic table, he actually has an atomic number of 6, which is that whole number, means that he has 6 positive protons. He has an atomic number of, and we're going to call that atomic number of 12. But this is another way to go ahead and call an isotope, or to write an isotope. Carbon-14. Now that 14 number is the mass number. don't forget that mass number is the addition of all the neutrons and the protons that that element is going to have. But it doesn't matter which type of isotope. Again, I know it's a review from chemistry class, but all carbons, whether it's carbon 14, carbon 15, carbon 16, carbon 17, whatever carbon, that carbon is always still going to have 6 positive protons. The number that does change is the neutron number, okay? So the neutron number would change in that situation. When we look at this one over here, carbon number 14, which is another way to write an isotope, it shows that if we're writing it in this situation or this format, we would say 14, 6, and C for carbon, right? So the mass number goes on top when writing that isotope. But sometimes you can see it like this, or it can be seen like this. Man, that pen is dead. There we go. So it can be seen either way. I just want to make sure that I'm very clear on that so students don't get confused. It says here an aluminum atom with 14 neutrons, okay, got it. Aluminum has 13 protons though, okay, or I can come over here to the periodic table, look at group 13, and I can see that aluminum has 13 protons. So in this situation, when I'm going to write this one out, I'm going to go ahead and say aluminum, Al, because that's the symbol for it. The 13 is going to go at the bottom when I'm writing this isotope because that's the atomic number. And then it says here, though, it's got 14 neutrons. So the number that goes on the top is the mass number, which is the addition of the neutrons and the protons. So when you add that 13 plus 14, hopefully you added it and you got the number 27. And that would be the number to go on top. Easy cheesy. Easy cheesy. So it keeps going on, and it tells us or gives us another example over here, right? And it says we've got BE and BE9. I can go to the periodic table to the number 4 because that's the atomic number, which is 4. Come over here, I can see that. And it says beryllium, it says here is going to have, let's see, 4 protons because it doesn't matter which isotope of beryllium. They're all going to have 4 protons. But in this situation, 9 take away 4 is going to be 5 neutrons, right? Easy cheesy. Like, oh man, Miss Munson, we got this. I'm sure. But we're going to do it again. It says, though, what if we have another beryllium? We got a beryllium, another BE, but this is BE10. Again, I don't care if it's BE10 or BE9, BE11, BE whatever. It's still going to have 4 positive protons, but in this situation now, I'm going to go and get 10. Take away 4 equals 6 neutrons. Like, this is such an easy question. We can't miss this one. All right, we can't miss this one. So the next topic here is binding energy, and I'm not sure if this is a topic that you talked about in chemistry or not, but binding energy is super important when it comes to not just chemistry, but physics as well. It's really all of this energy that's inside of the atom that's super important to us. It says here that when the masses of the individual particles of a nucleus are added together. Let's see. The sum here, it says, is going to be less than the nucleus itself. This may not make sense yet. Let's talk about it in practice for a moment. It says, for an example, well, we have an isotope of hydrogen, and this one isotope, not all isotopes have particular names, but this isotope, he actually has his own name. So, D-E-U-T-E-R-O-N. I know. That's his actual own name. Rather than just calling him hydrogen whatever, he actually has his own little name. It says here, though, this hydrogen isotope, yes, it's a hydrogen atom, but it's an isotope of this hydrogen. This isotope here has 1 proton and it has 1 neutron. Hydrogen atoms normally have, oh, let's take a glance real quick because it's like the smallest element on the periodic table. It's right there. And this is my traditional atom then I can see that hydrogen has an atomic mass of 1.008. This number is definitely not going to round up. We're going to leave it as 1, right? Again, why is it a decimal point? Because it's an average of all of the isotope hydrogens out there. But if I cover that up, it has a mass of 1 and it has an atomic number of 1. That atomic number is going to be the number of protons. The mass number, right, is going to be the number of protons plus the number of neutrons. So 1 take away 1 is traditionally would be 0. So in this situation, normally it's going to have, it says here, they normally don't have a neutron, right? We just did the math. It was 0. It's pretty simple, right? 1 take away 1, 0. It says here, they are just, it says, a single, traditionally, proton. But this isotope must be an old atom, because traditionally, if it has just 1 proton and 0 neutrons, and in that situation, it does have 1 neutron, that must be an old hydrogen atom. Like how old? I don't know. Ice Age old? I don't know. Direwolf old? I don't know. Is it, dinosaur old? I don't know. But it's old. And it has 1 neutron. That's it. And so its mass for this situation is going to end up being a 2. But let's look at the actual, what we call binding energy of this. The following, it says here below, what we're doing is we're adding the particles up of the atomic masses. Now, one more time, remember what we said over here earlier. I'm so sorry, I'm going to scroll back over here. But eventually, atoms become old and they become less stable. And the reason why they become less stable is because they're taking on these neutrons. Now, when they take on a neutron, have you ever gone through, like, let's just say, I don't know, Easter barbecue dinner at somebody's house? You've got the paper plate and you go through the line and you continue to add food. When you get to a certain point, you probably might need to switch your hands, how you're going to hold the plate. You might need 2 hands or more energy involved, or you might need to focus or be a little bit more cautious on your hand so that way you don't accidentally drop it. The same thing over here. These atoms they need more energy, they need to be careful. They don't want to drop a neutron. They have to hold it together, and if they drop a neutron, that's a lot of energy that's going to happen, okay? But it takes energy to hold that neutron in place, if that makes sense. And we call that energy the binding energy, to hold it together, even though it's so tiny that we can't even see it with our eyes or a magnifying glass or a microscope. That's how tiny it is. But it says here, here's actually the mass of what 1 proton is, and this is actually true story, the mass of what 1 neutron is. And so when I add these 2 masses together, I'm going to get 2.01 blah, 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 AMU. Ooh, do you remember what AMU is from chemistry class? Atomic mass unit. So you're going to get this, and that's the SI unit for it, the atomic mass unit. It says here, what is the total mass for a proton and a neutron? Well, I just got those 2, and when I added those up, it was right here of 2.016490 AMU. If the original mass was 2.014102 AMUs, what did you notice about the mass of the proton and neutron combined after, the separation? Then compare those before and the after. Now what happens is between these 2 numbers, because they are very, very small numbers and kind of like long because they have a lot of numbers, but I've got 2.016490, 2.01, whoa. Okay, 0, 1, 4, okay, and this was originally a 6, but this is a 4.102. It looks like my number decreased or got smaller. So what happened? The number decreased, or the mass, that particular number is a mass number, decrease. Now we call this mass defect. Something's going on here. And not only that, but something's going on with that energy. That energy, like how much energy did I lose or did I have to take in? Where did that energy go? Oh, now we're taking this to the quantum level. Where did that energy go? It says here, how does the mass defect defy the law of what we consider to be the conservation of mass? So let's look at this. Looking at this part over here, using Einstein's equation, E equals mc squared, and I know I talked about it, but here it is now on our notes, E equals mc squared, explained what happened to the missing mass. So Einstein states that if you get a certain amount of mass, like, I don't know, let's say we get a train. We get this train and we get it to travel at the speed of light, which is pretty fast, but not only that, we square it. That's how fast it's traveling. We can convert this mass into energy, and we call that mass defect, or the binding energy that is holding it together. That mass is going to disperse. Where did the mass go? That's what Einstein's E equals mc squared states here. The mass is quote unquote gone. Whoa, mass can't just disappear. We're not magicians, and it really doesn't happen in real life. It's somewheres. Well, Einstein says we can quote unquote cause mass to disappear, but what actually happens is that the mass is converted into energy. It says here, explain what happened to the missing mass. So what actually happened to the missing mass, or we call it mass defect, is when the hydrogen atom was separated into a single proton and a single neutron. Doing this took energy. So the mass itself, like if this was the mass, and when they separated, the mass changed, mass defect, and energy was released from it, okay? That's when they started thinking, oh man, can you imagine if we did this on a bigger scale, like atomic bomb scale? This is when they started thinking, oh man, can you imagine if we do this on a bigger scale, like a nuclear power plant, so we can get energy from uranium pellets? Like, they started really, this is where they started going with that. It says here that this energy is called the binding energy. And it says here, let's go ahead and let's take a glance at this binding energy. So, next page, so that way we can kind of help explain this. It says here that binding energy is the difference between the mass energy of the nucleus and its particles that it contains. It says here, though, to separate the nucleus itself into the protons and the neutrons, that energy, it says here, is going to equal that binding energy that was holding it together in the system. So how many protons separated? I mean, we were just looking at a hydrogen. I mean, what if we go now and look at a sodium atom or a uranium atom? Now we start looking at these big, heavy atoms that have a lot of protons. They have a lot of neutrons, right? And now when we start to separate them, now we're talking like, whoa, this is going to be major energy that's being released from something so tiny that we can't even see with our own eyes. It takes that much energy to hold it together, okay? So it says over here, let's go ahead and let's take a glance at another one. They said, let's look at this isotope, helium-4. Okay, well, just in case, I want to make sure that I write it out for us for helium-4, those of us, because if that's a question later on, like on a quiz or something, I'm just going to come over here and I'm just going to write it for us. How would you write this isotope of helium-4? Okay, helium, going to the periodic table, here he is, He, helium. And then coming over here to the periodic table, that atomic number of 2, which is never, ever, ever going to change, we're going to write that at the bottom, 2. But they told me this helium has a mass number of 4. So just in case, if the question says, write the isotope of helium-4, you would write it like that. The mass number goes on the top, right? And the regular atomic number, which is just the proton number, still goes at the bottom. And then we would write the helium. So I just wanted to make sure we're all on the same page. It says here, though, this helium-4, how many protons and how many neutrons does it have? Well, looking at this helium-4, it has 2 protons because it tells me that right here. And 4 take away 2 equals 2 neutrons, right? Simple math. You got this. Definitely want to use a calculator for all those decimal points, though. Oh, don't want to hand write that out. It says here, though, what is the total mass when separated? Okay, well, if I get this 2 times 1.007825, like I said, I would definitely use a calculator. You might want to double check my math, but 1 times 2 is 2 point, and I'm just doubling those numbers, 0.1565, and then 1 point, well, 1 times 2 is 2, and I'm going to double these numbers, 0.08665, well, multiply it by 2, I think it, double check my math, 0.1733. So the mass of the protons for this helium isotope is this much AMU. The mass of the neutron for this helium isotope is this number AMU. The total mass, if this helium atom was to separate, which we can cause it to separate if need be, when we do that for this situation, then we're going to get these 2 numbers over here, add them together, and that mass completely comes up to 4.03298 AMU, atomic mass unit. I apologize, let me scroll down a little bit for us. There we go. So, super easy cheesy. We can so do this for homework number 2. That's easy. We'll go back and look at homework 2 too in just a moment since we have a little bit, we have plenty of time. If the mass of helium-4, bless you, nucleus, when it's together though, but whoa, wait a minute. Let's say we did get this isotope and we got helium-4. We took him, here he is, and we put him on a scale. And when we did put him on a scale, he came out to 4.00290. Whoa, wait a minute. There's a difference there because when I just calculated it with my calculator and basic, math skills over here, I got 4.03298. There's a difference, okay? Something is not right. This is where we're saying, hey, whoa, that law of conservation of mass that you've been taught your whole life, where however much mass I start off with, I should end up with the same amount of mass. There might be a mass change if you have an atomic bomb that goes off, okay? And what happened to that mass? It got converted to energy because atoms were separated. That's the physics portion of it, okay? That mass, whoa, I just had an atomic bomb. Definitely not going to toss out my, had an atomic bomb. Oh, this is perfect. I have an atomic bomb here, right, with atoms from the periodic table, and it's all bunched up. And when I toss my atomic bomb, and then everything separates, right? The protons and the neutrons come apart. I lost some of the mass. The mass came a little bit different. What happened? Some of that mass got converted into energy because it takes energy holding it together. That's the physics portion of it, okay? That's the physics portion, right? We needed a dramatic example. I guess I could have had a little atomic bomb video. There you go. That was better, though. If the mass of helium-4, though, this nucleus, when it was added together, is 4.00290 AMU, what is the mass converted into what we call binding energy when the nucleus was bound together? Well, in that situation, I'm going to come over here because I write too big. Me personally. You may be able to fit it all in there. 4.03298 AMU. Subtract, there was a difference, 4.00290 AMU comes out to 0.03008 AMU, and we call this mass defect, meaning that there was some mass. We had the atomic bomb, or we had these atoms, and when we did that, protons and neutrons were separating, and there was some quote-unquote loss in mass. This is how much mass was lost. But we know, okay, that it wasn't necessarily lost. It was what? Transferred from mass to energy. That's it. And that's the physics portion of it. Pretty easy cheesy, I hope? I hope so. Now, on homework 2, it also has a little bit part of radioactive decay. And radioactive decay, I'm not sure if you talked about that in chemistry class. I apologize if some of us seems like this is a review, but let's go ahead. We have plenty of time to go ahead and keep going with this. That way, homework number 2 would be no problem for us. So, radioactive decay. Looking at radioactive decay, it says over here that isotopes. Isotopes of an atom can be stable or unstable. What do you mean, Miss Munson? Well, we're going through and we're at a barbecue at somebody's house, or we're at a family Thanksgiving dinner, and we've got that paper plate or whatever that they gave us, and as we're going through the line, we're able to either put just enough so that paper plate can handle the mass, or maybe it's a little bit unstable, so we might have to be a little bit careful with it. So some of them can be stable, okay? Some of them are unstable. Again, why are they unstable? Because there's too many hydrogens in there, okay? Because there's too many hydrogens in there. Now, we call these radioactive isotopes. Whoa, these isotopes are becoming unstable. They're radioactive. It says that a nucleus is unstable if it contains, and I've already said this 1,000 times, too many neutrons. Oh, that's a great quiz question. Super good. Right? An atom is going to be unstable when there's too many neutrons, or you're over there, at Christmas dinner, that paper plate is unstable when you have too much food on it. Makes sense, right? It's just too many neutrons, and it can't hold it all together. It says here, and or protons. Right? I mean, it's got to have protons. Protons are in there too. But it's that neutron number that can come in or leave out. Those protons can never come in or leave out. It says here that the unstable nuclei will try its best to become more stable. And it's going to try to become more stable by, it says here, ejecting or getting rid of particles. That's like Juan saying, okay, it's Thanksgiving dinner. He has a full plate of food. We can imagine it, visualize his full plate of food. And he wants to get some rolls. Juan, are you going to put the rolls on top of the plate? Or what would be a better idea so you don't lose the full plate of food? Okay, I was going to say get a second plate. I love that answer. He's a thinker. He's a thinker, yeah. He ate some of it, right? Because he had to get rid of it. He had to eject some of the food. That works good. He had to eject some of the food off of his plate. So, okay, I do that too sometimes, right? It's like, oh, I got to try it. I'm hungry right now. Let me try it real quick. So you can eject it by then, or you could have got a second plate and put some of those biscuits or rolls or whatever it was on the side. Either way, you had to eject some of it off of that plate because that paper plate can only contain so much mass. You know why you got to wash all these dishes on Thanksgiving? These are paper plates. It says here the process of ejecting these particles, though, is what we call radioactivity. Now, the problem is some people think that quote unquote radioactivity is super, super bad, and no one's gonna turn into the Hulk or a Spider-Man or anything like that. Like you're gonna be okay, because some radioactivity is not bad at all. So we're exposed to radioactivity all the time because elements on the periodic table are always unstable. Radioactivity emissions, it says here, of the particles from the nucleus, it says, from the nucleus of mass is the form of what we call the alpha particles or the beta particles. Sometimes I can't even speak today. Accompanied by the emissions of energy in the form of gamma rays. Oh, now that we're going to get a little bit on the bad ones. It says here that radioactive decay is a random, that's where we get to the physics portion of it. This is a random thing. I don't know always if it's going to be an alpha decay or if it's going to be a gamma decay or a beta decay, because it's random. However it decides to break apart. Okay, Juan's not in here right now, but however, I don't have a clue what Juan is going to eat. You know what I mean? So that way he can make his plate more stable. Is it going to be a piece of biscuit? Is it going to be a piece of turkey meat or, or something? You know what I mean? Like, he's going to eat something, he said, perfectly good, which is smart. He's a thinker, right? So that way his plate doesn't become too heavy. But it's random. I don't have a clue what he's going to eat on there, okay? Or what he's going to take off or eject. Same thing here. When radioactive decay occurs, we don't have a clue on here of what's going to happen. It's a random process, and it's spontaneous. It's spontaneous. Truly, we kind of have a rough estimation of how much time that it takes, but deep down inside, it can do it whenever it wants to, just eject these neutrons out of the way. It is very random. Okay, it's a spontaneous, random process in which it says here, an unstable nucleus will disintegrate, I can't even speak today, into more stable configuration by the emissions of what we call the alpha particles or a helium nuclei. It emits a helium, especially if we're talking about big elements. Let me go back to that periodic table. If I'm talking about these big elements over here, like uranium, they can literally, when they are going to eject something spontaneously, they can literally eject a whole helium nuclei. What? Seriously. What is that? What's a helium nuclei? What does that contain? Protons and neutrons, not electrons. Oh, okay. Keep that in your mind. Okay. Then it says here, which we call alpha particles, comma, beta particles. Beta particles are going to be, oh, wait a minute, electrons. Oh, remember? I know Miss Hudson, I don't remember. But if one is the helium nuclei and a nuclei or the nucleus of any atom is protons and neutrons, the other one, which is the beta, is going to be the electrons. Okay? So alpha is going to be a helium, which is protons and neutrons, and then a beta is going to be electrons. Then we have our last type of radiation, which is called gamma radiation. That gamma radiation, it says here, is going to actually be a short, quick, very high frequency wavelength of electromagnetic waves. It literally shoots out energy, right? Because waves are energy. It says here that some nuclei, it says, are unstable and spontaneous. And they'll emit radiation, which is called, it says here, radioactivity. Radioactivity. And since we still have a little bit more time, which is great, so that way we can handle homework. Says here, let's look at the next topic, radioactive decay. So, looking at radioactive decay, says some nuclei are unstable. Okay, well, we already said that. And decay, what does unstable or decay means? It means it's going to break apart. And when it breaks apart, it can be an alpha break, it can be a beta break, or it can be a gamma break, whatever. All right, those are the type of decays that it can happen. Alpha, one more time, beta, and gamma. Alpha decay, the shortcut for it looks like that. An alpha decay. I'm going to turn the page and I'm going to do the beta real quick. The beta looks like, and then I'll go back. Looks like that. Looks just like kind of like a capital B. Looks like a capital B. And then the gamma looks like a really weird, squiggly, upside down lambda. Looks like a Y, but it's kind of squiggly. I guess it depends on how you draw it. Here you go. It looks a lot better over here. Alpha, beta, and gamma. Looks a lot better than the way I did it. Alrighty, here we go. Back to the alpha decay. It says the alpha decay is when the nucleus, it says here, emits an alpha particle. And an alpha particle, which I kind of gave you a little summary over here, consists of what we call a helium nucleus. Whoa, what would that be? What would a helium, well, let me just in case, I'll pull up the periodic table. A helium nucleus. Here we go. A helium nucleus, which would be the nucleus, which contains protons and neutrons. Since it's the nucleus, then there's not going to be any electrons, right? And so I can see that the atomic number is 2, so it's going to be 2 protons. And I can look to see the mass is 4, so it's going to be 2 neutrons. So over here in our notes, it's going to consist of 2 protons and 2 neutrons. That symbol is going to look like this. This is an alpha decay. It says over here, in any decay, the atomic number must be conserved. We can never change that number. Conserved. Conserved. And what does the atomic number consist of? Number of protons, right? The atomic number. It's like the driver's license number. It's never going to change. So it says there's a conservation, it says here, of the charge. And in that situation, the mass number must be conserved so we can have a conservation of mass. It emits out a helium. It says, let's look at an example really quick. I've got a uranium, just in case, for those of us who, it's on the periodic table, and here he is over here, unstable. There he is, uranium. I've got a uranium-238. Now, wait a minute. I'm going to pause real quick, and I'm going to look over here. Uranium on the periodic table is 238. We would not round that up. Okay, 238. It says here it undergoes an alpha decay, producing a thorium. Wait a minute. What? 2 protons. The number changes by 2. Okay? So in this situation, let's go ahead and write out this decay. This would be uranium 238. The atomic number goes at the bottom. Oh, that's 92. Okay. So it's going to go through a decay, kind of like whenever you did a decomposition type of reaction in chemistry class. So I have my yield sign, and it's going to produce, what is it going to produce? It's going to produce all alpha decays produce a helium. Remember, the mass number goes at the top, the atomic number goes at the bottom, helium, and they even told me what else is going to produce. Now, they don't have to tell me that because they told me that mass is conserved. And since it's conserved, then the numbers at the top on this side of the equation must equal the numbers at the top of this side of the equation. The numbers at the bottom of this side of the equation must equal the numbers at the bottom of this side of the equation. So if it's 238 take away 4, well then that number comes up to 234. And 92 take away 2 is 90. And my symbol is TH. Yes.
You have to have the helium first lead.
You don't. I just wrote it first. Good question.
It's always going to be there.
It's always going to be there in an alpha decay. It's always going to be there in an alpha decay. So super good question. I mean, I personally write it first because I know it's going to be a guarantee. So since I know it's going to be a guarantee, I just write it first, and then I can do my math to figure out who this person is going to be. Because 4 plus 234 equals 238. 2 plus 92 equals 92. Not bad, easy cheesy. Let's look at that beta because it's also going to be part of the homework as well as the gamma. And so I want to make sure that we finish these so that way we can have this information. It says here that notice that the mass number on the right side of that equation that we just talked about equals the number on the left side because there is a conservation of that mass number. The next one over here is a beta decay. A beta particle is emitted. And what a beta particle is going to be just electrons, particularly one electron. I'm going to come over here just in case for later on for those of us who are going to look at your notes. One electron is emitted during a beta decay. An electron has essentially, well, no mass. Hopefully we remember that from chemistry class. It essentially has no mass compared to, it says here, to a proton. And a negative charge is what it does have. So the symbol for my electron is this right here. 0 at the top because it has no mass. A -1 because that is the charge of it. So it says here, let's look at this example of carbon. So carbon 14, oh, wait a minute. Carbon 14 goes at the top. Go to the periodic table. Atomic number is 6. That goes at the bottom. It's going to go through a beta decay, and on this beta decay, it's going to always emit an electron. So in that situation, 0 at the top, it's going to be a -1 charge, and it's going to be an electron is what it spits out. Plus, whoa, wait a minute, we do need to do a little bit of conservation here. Now, when we're looking at the conservation, did the top number ever change? 14 take away 0 is 14. Wait a minute. 6 take away -1 equals, do we remember this part of chemistry class? This is a 6, which is a positive number, but this is a -1 charge. What is a -1 charge? What is an anion? Do you remember that anion charge? If that atom becomes an anion, then does it gain electrons or does it lose electrons? An anion. And so if it loses electrons for an anion and have a negative charge, wait a minute. If it's a negative charge, does that mean that the protons leave, or is the electrons are the ones doing the moving? Who's doing the moving on ions? The electrons are doing the moving on the ions, right? Never the proton number. So if I've got 6 here, and I know this is a little weird, but 6, and I have a -1, all we do here is we say 6, take away a -1. What about taking away a negative equals a math class? 6 take away a -1 equals a, say it. Thank you. What is that 7? I know, see that flash? There's no even lightning. We'll survive it. Here we go. You did it. What is 7? Who is 7? Nitrogen. Nitrogen. So if there's anything that says a gamma decay, we're just going to stop our homework here. Just in case, if the homework number 2 has something to do with gamma decay, we're just going to